Thanks. So yeah, I'm going to do some graph theory. The advantage of the graph theory is that you have seen it more recently. The disadvantage is that it might be a little harder to know how solid you are on stuff, with that stuff at this point. So this review is going to help you decide that. So here's number 6. By the way, you're probably wondering by now how many questions I actually have. I have like 10 questions total. So, number 6, if G is a connected planar graph with at least 5 regions in its representation, what is the minimum number of vertices in the graph? Okay. So, you read the question, you don't have it all figured out right away probably, but you kind of have an idea what we're talking about. This is the material we just covered, right, on planar graphs. And we're talking about number of regions, and we're talking about the number of vertices and so on and so forth. So can you guys tell me what are some relevant things that we've learned that might be, and I'm not going to hold you to it, but that might be helpful here? Go ahead. What's that called? You guys are helping each other out a lot. I don't know. No, that's fine. I don't care. Yeah, it's Euler's formula. Just so you know, there's not going to be a team test on Monday. What? You didn't know that? I don't think it's on. I can tell you're having fun with this.
Last time you taught 407, did you do group tests?
I don't think so. I don't remember.
What was the first exam on then?
Huh?
What was the first exam on then if it wasn't a group test?
Oh, I get it now. I'm a little slow.
Nice.
Very nice. Okay, what did you say the formula is?
R minus E plus N equals 2.
Beautiful. Okay, so that is Euler's formula. That seems like it might be relevant because we're talking about number of regions, number of vertices, and so on. Okay, so we got that. Anything else might be relevant that you know of?
E is less than or equal to 3n minus 6.
3n minus 6. Because we know it's planar, we are assuming, you guys be careful, what are we assuming and what are we showing? We are assuming G is already planar, so that equation is already true. We know that. Okay. So we have that, and then what else do we have in the given information? What is at least 5? R, right? Number of regions is at least 5. So here's a lot of good information to get us started. Now, can I use the 2n minus 4 inequality on the edges? In other words, the improved formula that Mark gave me? Unless I said there are no 3 cycles in the graph, then you can't use that. So this one you're always allowed to use. This is the general one for a planar graph, for a connected planar graph. But if it's if there are no 3 cycles in the graph, then you could have used the 2n minus 4 inequality as well. But this is all we get to work with for now. Okay, so this is a little bit of a tricky problem in the sense you have inequalities, a lot of that type of thing going around, but I think we can still do some stuff with this. So what could we maybe do? So we know that 2 is equal to r minus e plus n. So we're going to get that 2 right there at the start. So I want to know where I'm starting from.
Would it suffice to show
Not necessarily. I don't necessarily know that the minimum number of regions correlates with the minimum number of vertices. That would have to be kind of explained a little bit. Yeah, Bora?
We do know that each region has, degrees without.
Yeah, oh, that's true too. Yeah, the regions always have degree at least 3. I have to put that in here somehow. And that's actually used to prove this. So in some sense, I could imagine that that information is already built into the inequality that Mark gave me. But it's good to have that in mind. That might be helpful. Let's see. If I take this R and I just replace this with the 5 that we just said. So the number of regions is at least 5. Can I simplify that or rearrange it or something? Okay, how do you want me to simplify this? What would be a helpful way to simplify it? Yeah, I could, okay, so I could take the 2 and the 5, I could subtract, right? I could simplify it. It's going to leave me with a 3 on this side. Yeah, I don't like to subtract anything. Let's make everything positive. So E is greater than or equal to 3 plus N. Does that maybe help a little bit? Yeah, Lisa?
Now we know that we can write 3 plus n is less than or equal to e, which is less than or equal to 3n minus 6.
So we actually can put all of those together. Oh, wow. I think we just finished the problem. You just came up with the right thing. Because look, if I just kind of ignore this one and just compare this with this, can I just get an inequality? What am I trying to come up with, by the way, at the end of this problem? A minimum number of vertices. That sounds like n should be greater than or equal to something. Can I get n greater than or equal to something now? At the 3 and the 6 combines to 9, right? Less than or equal to 2n. So n is at least, anybody? 4.5. Can I have 4.5 vertices? You always have to pull numbers up to whole values. So n is at least the ceiling of 4.5, which is 5. You have to have at least 5 vertices. I wonder if we could draw that. Can we draw a graph that has just 5 vertices, that has at least 5 regions? And connected. Yeah, it has to be connected. I don't know. It's not telling me how many edges to use, so that's fine. I know I will use less than 10. Otherwise it won't be planar anymore. So there's 5 edges. So if I just do this, 1, 2, 3, 4. I need how many regions? I want at least 5 regions. What else can I do? Could I do this?
No.
Don't get fooled. That curvy edge is joining the same 2 vertices as this one, and it's no longer a graph. Now you have a multigraph. By the way, does any of this stuff with planar graphs and so on, does it apply for multigraphs?
No.
It doesn't. You want to know why? Because if you have 2 edges like that, then you supposedly have a region here of degree 2. And one of the very fundamental premises that we were using throughout our derivation of all of our facts is that we have regions of degree 3 or more. So we're not going to do multigraphs. So this edge, and I think also in the homework you proved a problem that said, well, if you have a multigraph and you have multiple copies of an edge, that doesn't really affect planarity anyway, so you may as well delete multiple edges. Just reduce down to this. So okay, so that didn't work. So what should I do?
Connect the top one to the bottom one on the outside.
way out here?
Yeah.
I think that does it. Because those edges were not, those vertices were not connected before. So now you've got it. Okay, so there you go, 1, 2, 3, 4, 5 regions. Okay, does this seem okay? All right, I got another problem for you. Come over here again. See, some of these graph theory problems are fairly quick. You're not doing a lot of heavy calculations. Number 7. Draw an example. Aha! I could ask you to do this. I'll leave it open for you guys. Draw an example of a connected graph of order 7 that has no Eulerian trails, no Eulerian trail, no Hamilton cycle, and is not planar. I want you guys to try it. Give you a couple minutes to see if you can do this. You need 7 vertices. I want there to be no Hamilton cycle, no Eulerian trails, and I don't want it to be planar. And then we'll talk about how we would create that. Did you get it, Joseph?
I think so.
Jeez, that was fast. I didn't think it'd be that easy. Isn't that easy? Oh, shoot. That actually is pretty easy. You want to draw?
If I'm thinking about it right, sure. If I'm not, then
we'll all just make
Yeah.
fun of you.
of course.
Let's see what you got. It'll be interesting to see if he's got the same thing I've got. Okay, thanks. So look what he did. He created a graph that has K33 as a subgraph. What do we know if K33 is a subgraph? It's not planar. So he's got that part of it already for sure. Not planar. He's got 7 vertices. No Eulerian trail. Let's see. How do you figure out if something has an Eulerian trail?
They're even?
For an open Eulerian trail, let me come back to Anthony's point. If there's an open Eulerian trail, there will be exactly 2 vertices of odd degree. But for a closed Eulerian trail, they would all have even degree. So remember, there's open and closed, and you have to know both conditions. So all you have to do here is just look at the degrees of the vertices. You've got 3, 1, 4, 3, 3, 3, 3, right? So you have tons of vertices of odd degree, way too many. So there's no Eulerian trail. What about a Hamilton cycle? Yeah, if you have a bridge in your graph, right, he's created this bridge right here, actually. A bridge is just an edge that disconnects the graph after you take it out. Then you will have a problem because you can't get back to that vertex again. Basically, this edge is the problem. That's really good. It's Joseph, you did basically the same thing I did. The only thing I did it with K5 instead. I just put my K5 there and then just made some things sticking off the end of it. 2 things sticking off the end of it.
That always sticks.
Oh yeah, I have to have 7 vertices. So yeah, so I just did 2 things sticking off the end of the log. You see that? Okay, so this just is a good time to remind you that if you have a K3-3 or a K5 inside of whatever graph you're drawing, it won't be planar. So if I ask you to draw something that is not planar, please think about doing that. Think about creating a graph that at least part of it is a K3-3 or a K5. Okay? All right, let's do a quick follow-up on that. Follow-up is I want to do the exact same question, but this time I want to do one where the graph is planar. Okay? So same as above. Same as above, except I want the graph to be planar this time. So I'll give you guys another couple of minutes to see if you can draw. 7 vertices, no Eulerian trails, no Hamilton cycle, but it is planar. You want to draw one? Come on up. Lisa thinks she has it. You guys can keep working on it though. There's probably lots of right answers. All right. Got the fan-shaped graph going here. So one vertex, well, it's a tree, right?
Yeah.
One of a good example of a tree. So you have a vertex at degree 6, all of the others have degree 1. Okay? So clearly there's no Eulerian trails because we have too many odd degree vertices. Definitely is planar. There's no Hamilton cycle. Okay? That's not too bad. Everybody good with that? Yeah, Adriana?
Any graph that is isomorphic to that one, does it also not have a Eulerian trail?
Right, right. Isomorphic graphs always share the same properties, and you're just going right into the direction that I'm about to go in.
Oh, okay.
Yeah, because I haven't talked about isomorphisms yet. Yeah, if you have 2 graphs that are isomorphic, they will share all of the same properties. Planar, Eulerian trails, Hamilton paths, blah, 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 blah. They will have all of those properties. Let me give you an example of one of those, actually. I've only got like 2 or 3 more problems to go here, but I think this will be a good one. I'm going to switch the order from what's in the handout so I can follow this one next because I think it would be good. Okay, so if theta from G1 to G2 is a graph isomorphism. By the way, a lot of times what we do with isomorphisms is I give you a graph, I give you 2 graphs, and I say, are they isomorphic? Yes or no. You'll see those in the review packet. This one is a little different, but I think we can all handle it. So we take a graph isomorphism, and G1 has a Hamilton cycle. Prove that G2 has a Hamilton cycle. Now guys,
We can't just say that because they were the same properties.
right, I'm asking you to prove that that is true here. You've heard me say it before, that graphs, that isomorphic graphs preserve all of the same structural properties, but we haven't always proved it, all of those. So now's our chance to prove this one. And guess what you're going to think about doing when you're studying maybe tomorrow is how many different words could I change the Hamilton cycle to that I could practice on? And that just depends how much time you have. So in other words, if G1 is bipartite, then G2 is bipartite. If G1 has a closed Eulerian trail, then G2 has a closed Eulerian trail. Pick your favorite word, put it in there, and prove it. So we'll do this one here. You'll get the idea. And then you'll see that it's the same structure for all of them. Okay? I'm just giving you suggestions because you never know. I mean, I could just literally take this problem and change Hamilton cycle to something else, right? And it would. This is going to give you the idea of how to do it. Okay? So here's the solution. We're proving that Hamilton cycles are a structural property. So if on the test you have two graphs and you can see that one of them does have a Hamilton cycle and you can see that another one does not have a Hamilton cycle, then you'll know that they're not isomorphic. In fact, I could set up a problem like that. I could say, here's a graph, give me a Hamilton cycle. Here's another graph, prove that it doesn't have a Hamilton cycle. Now part C, are these two graphs isomorphic? And you'll be able to just say no, because it's a structural property that Hamilton cycles are preserved by graph isomorphisms. You see how nice that would be? Like writing this test in my head as I go. It's a great question.
Just repeat.
Okay. I get so excited. You know, one of my problems, I've had this problem for years as a professor, which is that when I think of questions for the test, I usually want to just tell you like right away, because it's like, oh, that's a great question. I should tell everybody how to do that problem. And then I never like stop and hold back to let somebody else actually solve it on a test. So I have to restrain myself. Anyway, I will restrain myself. I will do this problem, and then I'll move on. Anybody have a suggestion? Let's see. Got a graph isomorphism. G1 has a Hamilton cycle. I've got to prove that G2 has a Hamilton cycle. We're going to need a whole bunch of notation. We're going to need to introduce some notation into this picture. Okay? Any thoughts? We need to set up the vertices, right? Okay, so for G1, assume V1, so this would be the vertex set. Let's just assume that the vertex set is, you know, x1, x2, up to xn. Okay? So we have our vertices. And actually, okay, that's fine. That's fine. Okay, so now what? Okay, well, we're given that. We're given the mapping.
Say G2 has G2.
Okay, so we have then for G2, we have, I mean, one thing we know is that the second vertex set has to be the same size as the first one because they're isomorphic graphs, right? We're assuming that these graphs are isomorphic. That means that they have the same order, right? So V2 would be, I don't know, Y1, Y2, up to Yn. Yeah, Maura?
We just call those theta.
And according to using theta, we may assume, I'll just do that here. We may assume, without loss of generality, that V2 is equal to the set theta of x1, theta of x2, up to theta of xn. Okay, so far we're setting up our vertex sets. And we're just assuming that that's the notation. Setting up notation is always kind of a painful part of this type of problem, but we have to do it. Okay, I haven't heard anything about a Hamilton cycle yet. I've got my two vertex sets, and I know that the first graph has a Hamilton cycle. So what should I do? Write the Hamilton cycle, exactly. So that the first graph has a Hamilton cycle, we should, you know how you do it. If I give you a graph and I say, give me a Hamilton cycle, you just sort of label the, you know, vertex goes to this vertex, goes to this vertex with arrows, right? So that's kind of what we should do here, don't you think? We may as well. Okay. So since G1 has a Hamilton cycle, we exhibit it as follows. And I'm going to go without loss of generality, and I'm just going to suppose that we go x1 goes to x2, goes to x3, goes to dot, 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 goes to xn, which goes back to x1 again. It's a cycle, so it has to go back to where it started. By the way, make sure that you use every vertex. Remember, the definition of a Hamilton cycle is every vertex has to be visited by this cycle. So notice how I was careful to use all of the vertices there, right? And I'm just assuming I've relabeled these vertices so they are in the order that my Hamilton cycle visits them. Are we okay with this? I know we've been at this a while. People are a little bit tired, but I just want to try and push through. This one isn't actually that hard to prove. We're just about done with the proof, actually. We've got the Hamilton cycle for the first graph. We've got all of our vertices figured out. So what am I going to do next? Let's see. I want to hear from some different people here. Rocky, do you have a suggestion for me? What's up? Not so far? Jason, how about you? Then we get, so you just want to start with, okay, go tell me, so theta of,
Goes to theta x2.
okay, this keeps on going. Theta x n, just like that?
Yeah.
Okay, that looks pretty good. I mean, here's our second vertex set. We've used all of the vertices. So it seems to meet the definition of a Hamilton cycle. So what do you guys think I would want to see explained here at this step? What should at least be stated that I've done? Mark?